So distance formula, how'd you do on that from memory? And the only reason I said from memory is just to make sure you're studying your notes. Shouldn't have to look it up at this point. D equals, what is it? You forgot the square root. x2 minus x1 squared. Yeah, you can. That's why you told me you can't see anything.
Well, if I close my eyes, I couldn't see.
Let's try this again. There you go. You will use the distance formula a lot in this unit towards the end for proofs, okay? So this unit concludes with proofs, just like the last two units have. And these will be the longest proofs that we do in terms of workload, but also they might click with you better because they're a little bit more algebraic in nature, sort of. But distance formula will be one of your main proving tools that you will use. So you, throughout this unit, if you don't know the distance formula or if you're prone to making mistakes with it, this is when you need to start really digging into it. What were some of the cautions with it?
No negatives.
What?
No negatives.
Yeah, like you should not, once you square, once squared, no negative. I really can't overstate that enough. This unit I might consider, if you leave a squared underneath your radical, I might just mark the whole thing wrong. No partial credit. Okay, so I just want you to keep that in mind because that tells me that you are, like you're kind of lost with even a basic number sense concept. So we need to get that fixed. So no, 1 squared, no negative. Also, I'm not going to keep this on here, but I want to point out there's subtraction inside parentheses and there's addition in between. Sometimes you get those mixed up. So don't. And then, of course, the squareds, don't forget those. Okay, midpoint. You forgot to tell me the left side. Remember, this is an equation. So we just average the x coordinates. And, yep, average the y coordinates. Does it matter what order you do x1, x2, y1, y2? No.
Isn't there, if there's more than one point, you change the bottom fraction to equal that? Like if there's like 4 points, you do find that.
Well, but we would never find the midpoint of 4 points, right? Yeah. All right, slope. We haven't talked about this for a little bit, or maybe not at all this year. How do you find slope? First of all, you use m for slope if you think back to y equals mx plus b from algebra 1. But what is this formula for slope? Remember how to calculate it? Okay, I'll give you this one. And I want to point out a geometry connection. So remember, it's just the difference. We said change in y over change in x, right? But check this out. Let's say you're doing a proof, and I know I'm previewing this. You're not there yet. But let's say you're doing a proof where you need to find the slope and the distance of several segments. Look what you just found right up here. See how that has y2 minus y1? Can't you just take that and plug it right in here for the slope? And same with the x, 2 minus x1. Or vice versa, right? You could find the slope first and then stick it in the distance formula. So this saves you a little bit of work because you'll be doing up to 6 distance formulas in one proof or 6 slope calculations in one proof. So we want to be efficient. We don't want one distance calculation to take 5 minutes because then the proof will take you 30 minutes. Okay? So again, we're working on getting better at that. But that's one of the nice things about this unit is there's connections between the calculations. Bisect means what? Yeah, split in half. I sure wish I could write. There we go. But the big idea there is this: two congruent segments. All right, so let's see if you remember this. Two parallel lines. I want you to think back to more along algebraic thinking. So we're back to like an XY coordinate grid. What is true about parallel line slopes? Well, true, the lines don't cross, but what's true about their slope? Same slope. If you don't remember that, write it down. Same slope. Perpendicular lines. See if you remember this one.
Yeah.
Okay, one line coming up, one line coming in. If you don't remember, that's fine. But there is a relationship between those slopes. Does anybody remember that?
Yes.
Okay. It's two things: opposite sign and reciprocal, which means it's flipped over. Okay, so if we have one slope that's 2, what is the perpendicular slope? Negative 1/2. So you just flip it over and it's negative, okay? Or go the other way. If I gave you a slope negative 1/2, flip it over and it's 2 over 1, and then it's positive. Okay. Start studying that list, please. It will benefit you by the time you get to the end of this unit and along the way a little bit. So wherever you wrote this, look at it tonight. Just look over it each night so that it's not going to take you 25 minutes to do a couple calculations. Great. This unit is all about quadrilaterals mainly, and other polygons briefly here at the beginning. But mainly it's about quadrilaterals. So we're going to learn the depths of quadrilaterals. No joke. There is so much in there that most people don't really think about. You're going to be able to recognize them, solve with them, prove that they are them, etc., etc. So what is a quadrilateral? Let's just start with a brief definition. What did you say? 4 sides. Okay. So quad and then lateral. Do you need to go? Are you good? Okay. Yeah. Yeah. 4-sided shape, which means it has 4 angles too, right? And so we're going to look at that in depth. For this first lesson, we're going to focus on this though. So we're going to talk about angle sums. That should ring a little bit of a bell. What angle sum theorem have we already studied? We've talked about one and used it pretty extensively. Angle sum theorem. There was one word in front of it. Man, I wish you guys would read your notes occasionally.
Still want to add. Angle addition function.
I said theorem. And you need this for today's lesson. So I'm giving you a hint. In fact, it's the exact same phrase except for the first word changes. Instead of polygon angle sum theorem, triangle angle sum theorem. Okay? It was not a trick question. What does it say? No. What does the theorem say? Not the words on the screen. Did I need to be? Okay. You need that for being able to figure out today's work. So triangle angle sums. Now we're going to say polygon angle sums. These are going to be more involved, just so you know. Obviously, we have more angles, so it can't just probably be as simple as that. Okay, so here's a question. Actually, I'm just going to use this screen. If a triangle has 180 degrees, can't see that. How many degrees does this shape have? What is this shape called, first of all? That's a pentagon. How many degrees inside? Do you think it's less or more than a triangle? Okay.
There's basically two triangles in it, so please double
Okay, I like that you're thinking that way. That is awesome. Let's go here first. How many degrees are in that shape? Why? Okay, so he's thinking specifically about a rectangle. What is this shape called? Trapezoid. How many degrees are in it? Is it the same as a rectangle? It does have 4 sides. So is it still 360? It is indeed, yes. I'm going to give you a hint. What if I connect this corner to that corner? What do you see? 2 triangles. How many degrees is in each of those? Okay, so how many degrees total? You guys said you think a pentagon has more degrees. We're going to see how to calculate that in just a second. But what is a polygon? Here's a definition for you. Okay, so straight sides, that keeps this from being things like the shape of a pill, you know, which is like a cylinder and it's 2 half spheres on the ends. But 2D, of course. It doesn't have curved sides. It only has each side only has 2 points of intersection. Poly means what? Yeah, multiple. Okay? So let's go define this in your notes. And you're going to have some definitions in this unit that maybe you feel like you know, which is good. Unit 6. Okay. But again, this unit is definitely mostly about quadrilaterals.
Is it easier or harder?
I can't really answer that. There's more in it. A lot more in it to remember. Here, I'll show you this quick preview if you want it. Ready? You're going to need to know all that stuff for each figure. Okay? Yeah, there are. Yep. You will have filled out one of those probably by midweek next week, maybe end of next week. And you'll start memorizing it. Okay, 2D. I'm going to definitely abbreviate that. A 2D closed shape with straight sides. We're going to talk, I'll show you the definition, but since we're here, let's just write it. We are only going to talk about convex polygons in this unit. Convex, has anybody heard that word in like physics or any other class? Are you guys just gonna like visit
I'm gonna use that.
and talking? Which is fine. Just step outside if you need to do that. Convex means all the points poke out. That's like the definitely not formal definition. So each vertex points outward. Okay. The other version is called a concave polygon. We don't study those, but you could think of it if you want. I'll just draw a quick one. Something like that. Do you see how two of the vertices point inside to the figure? So that is a concave polygon. We're not going to study those. So if we drew something like that, it would be more like this, right? Or all the points are sticking outward. Okay. So here's some examples of both of those. See the difference? All right. Now, this word is really important. You will have this word to guide you on test questions, and if you skip over it, it can cost you not knowing how to do it. So a regular polygon. All sides are congruent and all angles are congruent. Basically, this is like the prototypical one that you think of when you say octagon. Oh, that's a stop sign. Or like this one, right? Or square, or hexagon, or pentagon, like our building that's over in Washington. Those are the prototypes, the ones that look perfect. That's what a regular polygon is. But understand that I could draw some weird looking, like that. There is a break in the slope right there. That is a pentagon. Does it look like one? Heck no, not even close. But it is one because it has 5 sides. It is not a regular pentagon though, okay? So the regular version is the beautiful prototype that we all think of. And it matters that you know that, like meaning it really matters if you're told that it's regular. So let's put a star by this. Regular polygon. All sides and all angles are congruent. So this, just like subnote this. Okay. If I say octagon, how many of you think of a stop sign? And that's because all the angles and all the sides are congruent. It's not wonky, right? There's not 2 of the sides that are stretched out or something. So regular, again, that's going to change how we calculate some of these angles and stuff today. Anybody know the name of this guy right here? How many sides does it have? 7. Anybody ever named a 7-sided polygon before? Yeah, that's good. Okay, well, I think I have this later, but we're about to learn names of polygons. So, in your notes somewhere, don't create like a whole beautiful table. You could literally just do a T-chart and do sides, and then start with 3 and go up to 12, and then we'll just write the name on the side. Okay? I don't care where you write it. Yeah, just in there is fine. And this, you don't have to write it. Like, you could just memorize it. a lot of these you will be familiar with already. Be careful, I heard square on 4. Is every 4-sided shape a square? No. That's true. So that's like saying the converse, right? Like one direction's true, but not the converse. All right, so let's go through what is a 3-sided shape. Triangle. I think it's funny that it's got 3 sides and we say try like 3 angles, but that's okay. Okay, what's a 4-sided shape called? That's like the princess or whatever of this unit, the quadrilateral. Okay. 5-sided shape. Pentagon. Anybody ever been to the Pentagon? The building? You have? Was it cool? Nice. I've never been there. Okay, how about 6? Six is hex. Hexagon. Seven, that was the one we just saw, is a septagon. Sometimes also heptagon. So probably good to know both. 8, we've already said. What is 8? Nine. Anybody heard that one? Okay. Nonagon. It's kind of fun to say. Okay. How about 10? I bet you've heard this one. Yeah, good job. 10 is a decagon. Like a decade, right? DECA is a prefix for 10. Decade, decathlon, deca. 11, I'm pretty sure no one's heard of. Yeah, undecagon or maybe undecagon. I would think probably undecagon. But I want you to notice. Anybody ever played Uno?
Yes.
Yeah, they're like Uno in Spanish is 1 as well. So it's like kind of like adding 1 to a decagon, right? Like 1 plus a decagon would be 11. How about 12? Have you heard of 12? All right. Yeah, you're close. Dodecagon. And then we're going to stop there. And this isn't just our class. This is how we do this in mathematics. After that, there are names, but definitely don't need to know them. We're just going to call it an n-gon. Okay? Where n is... That was clever. The number of sides. So, like a 50-sided figure would be called what? Yeah. Like a 50-gon. A 50-gon actually has a name. It's a something pentacontagon, I think. But we're going to say 50-gon. Okay? Or a 22-gon or whatever. Okay? So let me just, before we move on from this slide, if I say how many degrees are inside of a nonagon, you need to know that it's 9. 9 sides. 9 sides affects how many degrees are inside of it. So up to 12, up to dodecagon, you'll need to know it by name. After that, we'll just number it. Okay, so you do need to know these. Any questions on them? Okay. Don't know why I have that in there. So let's go back to that idea I wrote on the blue slide. How can you find the total degrees in any polygon? On the interior, so total degrees on the interior angles of any polygon. Yeah.
Trying to find triangles inside of it, like the small triangle.
Yeah, perfect.
And then you
How
also
many
find-
triangles can we draw, and then what do we do with those triangles?
Add 180
Well, not add, but let's say we could draw 3 triangles. What would we do? 180 times 3. Okay. Man, you guys are sharp. Good job. So let's write it like this, just for now. Triangles. I'm going to say number of triangles times 180 degrees. That's going to give us the total of our interior angles. What we'd like to do is be able to turn this into some kind of a formula. In other words, if I give you a 22-gon, nobody's going to want to sit there and count how many triangles there are, right? So is there a way to figure that out where I can just tell you the number of sides and you're like, oh, this is how many triangles fit in there?
Yeah.
10.
I was gonna say like for every 3 equals is 1 triangle. So like
Sorta. Well, how many would you say goes in here then? Triangles. 2. Okay. One, 2, that's supposed to be straight. 3. So how many triangles are actually in there? 4. Okay. Now I'm going to give you a hint on how to make the triangles and then see if you can come up with the rule, this little formula over here. Pick one vertex and connect it to all the others. So I picked this top vertex. It was already connected here and here. So those 2 vertices were already connected. I just had to connect the other 3 vertices, and that made 4 triangles. Okay? So try that on these. How many sides? How many triangles? That's what you need to connect. Okay, I'll write that up here if I can get this to sit still. How many sides? How many triangles? And see if you can come up with a little relationship that we can use for every polygon ever. So again, you're trying to boil it down to some little formula for how many triangles we can make in a polygon.
I'm just trying to visualize it. Alright. Yeah, it's the same, but like, you know, it's not. Looking at, I'm not touching with my fingers right now. Counting the lines, not the triangles.
All right, there's our triangles. Remember, just pick a vertex, and after we figure this out, you won't really need to draw them anymore, hopefully. But pick a vertex and connect it, or make sure it's connected to all the other vertex points. Yeah.
So I'm saying
you actually don't have to draw them, but like, just because I figured out another way, is it when you choose your vertex, when you look at the opposite side lengths, you can just count each side length without having to draw and value data.
The ones that are not connected, you're saying?
Yeah, well, no, we can.
So like, let's look at this bigger one. You're saying count that one, that one, that one, that one, that one, that one?
Yeah.
Okay. The ones that are not connected to the vertex? Okay. That seems good. Again though, after this, we want to get to where we don't have to do this. Because if I give you a 50-gon, you're not going to want to draw in there all those lines. Plus, I'll show you one in a second. It looks like a circle, almost. You wouldn't even be able to do it. So, how many sides? After I start writing this super clear, I think you're going to figure this out. How many sides? First one. 5. How many triangles? 3. Okay. How many sides? On the top right. 4. How many triangles? 2. How many sides down here? How many triangles? 6. How many sides? 6. How many triangles? 4. So what is always happening? We're always subtracting 2. In other words, we can draw 2 fewer triangles than we have side lengths, right? How would we write that in a formulaic way? Because we don't want to write like 10 words. Every time subtract 2 from the side lengths, that would be a lot of writing. Because if we go back up here, this is the total degrees inside. It's 180 times something, but we just want, instead of the number of triangles, we want a formula there. Okay, perfect. Okay? So back to your notes. You guys figured it out? We're going to have 4 different angle formulas, so let's kind of clump them together. And we're calling these angle sums because we're adding them up. Hey, Trevor. Yeah. Remember, I have to go over there for a little bit, though, to the 100.
I have a meeting at lunch, so I might be able to come in at the end.
Okay.
I just had a question on the homework.
Okay, cool.
Thank you.
Yeah, no problem. All right. Interior angle sum equals 180 times are you guys, I don't like the way I'm writing this. Give me a second to scoot it over. Because I want to be able to box it. So interior angle sum equals 180. And then here's how we're going to write that discovery that you made. N minus 2, where n is the number of sides. Okay? If that works for you, we're going to have another thing called each interior angle measure, so I don't want you to get it mixed up. But if that works, that's fine. Okay, so interior angle sum, 180 times n minus 2. In other words, we can draw two fewer triangles than side lengths, right? In fact, why don't we put that on here just to make sure we're clear. Total triangles is n minus 2, and then times 180 degrees per triangle. Okay, just as a reminder of what this is. So n minus 2, that's the total triangles that we can draw. So interior angle sum of a 40-gon, what is it? What's the sum of the interior angles? Yeah. You're not going to do that in your head. So how many degrees are in a 40-gon?
Like 72.
I'm going to write that here. How many degrees are in the interior of a 40 gon? Okay, so it's just interior equals 180 times 40 minus 2. And what did you say that is?
7,200.
Okay. 7,200 degrees. That is way different than a triangle, huh? It's 38 times 180.
Yeah, 6,000.
All right, what is it? 6 what?
6,840.
Thanks, Tim.
Yeah, you're welcome.
Now we're good. Actually, did you forget to subtract?
Yeah.
Yeah, that actually happened. So make sure that was a good example.
I was paying attention to what was happening. So
No, you're fine. Okay. Next.
I was bored by the next one.
Yes, sir. Yeah. All right, go ahead and do these. I'm going to give you 5 minutes on them. Find the sum of the interior angles for each polygon. I heard you. I'm going to come.
If that's right, I get this.
Okay, so again, we're not doing these two. They're too easy. And also, we don't need to practice easy stuff 50 times. Okay, how many sides does the first one have? 7. So this is interior. And we're going to say 180 times 7 minus 2. 900 degrees. Okay, and equals what on the second one? What's it called without looking? No, a 10-sided figure. A decagon, good. Sorry. So 180 times 10 minus 2. I think that's what you said, 1440. Okay. How about this one? 9. Nonagon. Will you just unlock that for me? Thanks. Okay, this one is how many? Okay, couple things.
You missed everything.
Please don't focus on getting the number. Like, this is not the only goal we have here. I'm about to show you what I mean in a second, but notice how every time I've written this, I've written both sides of the equation, which is true. Every time you write a formula, you should always write both sides of it. Like for this class, but also for physics, science, whatever. Write both sides always. Again, we're not just focused on that number. Because what if I give you that number and ask you how many sides it is? Or something, right? And then we have to plug in differently. Make sense? Okay. Like that one. A polygon has a total measure of interior angles of 1800. How many sides does it have?
8.
So, do you see how we might have to plug in differently? Here's what I mean. We're not going to pause here too much, but here's what I mean. Write your little equation with both sides. And then where do we plug in the 1800? Nope.
The 180.
No, we can't plug in for a number.
You divide
Don't do the work. Just tell me where we plug in the 1800.
1800 at the interior.
We would have error too.
Y'all are so slow. Why didn't you get that?
Now, can you solve that equation for n?
Yeah.
Yes.
Okay, let's do it. How would you do it?
Subtract 180.
Holy cow, I'm about to walk out of this door. Subtract 180?
You multiply it to the end, you distribute.
180 and 180 and right, and then
Or we could just divide by 180.
Oh, yeah.
and then equals
Oh.
minus 2
Now what?
minus plus 2 and equals 12.
So this is a, what is it called?
12
Wait, no, fuck.
Dodecagon.
Dodecagon, yeah. Okay, all right. Don't get lost in the work. Write the formula, fill in what you know, and then solve for what you don't. Like, that is powerful mathematical strategy. If you learn anything this year, at least learn how to do that. It's like that's something you do in any job that uses equations or formulas, as they say. Even if maybe you're just monitoring temperatures of freezers at Walmart, you're going to have to plug numbers in something, right? So be able to plug numbers in where they go in a formula. That's like kind of like basic concept. Do we need to put that in your notes, that example?
Yeah.
After that, I think we should.
I think we should flip the coin for it.
Actually, I have.
I know only one of you is using this, but I'm still going to do it this way. Because it's whatever.
Yeah. You guys have a quarter. Why do you need a quarter? Why do you not?
Okay, why am I
Exactly.
what?
Exactly what Kenny said. Guys, if you're gonna go paint today,
I'm gonna be blown up like 2.
You would have to get a touchdown every second.
Okay, so there's your problem. How do we solve? One, you guys, I'm not sure what's going on. If you don't need the example, I guess that's fine. But write both sides of the formula. Again, I told you we're going to have 4 different formulas for angle sums. We're only on the first one. So this is interior sum equals 180 times n minus 2. Okay, and then again, this series of steps on the left side is not unique to this at all. Like, you could apply this to tons of different classes, even subjects. Plug in what you know. We know the angle sum is 4140. And then solve for the unknown. I'm writing out here to the side, know this process in life. Just know it. All right, solve. What's a good first step? And then, of course, add 2. Okay. So we're practicing plugging in both sides or writing both sides because this next version is a little more complicated. And if you don't write both sides, you can get lost in it. Any questions on that version though? Okay. Okay. So notice I've edited this a little bit, but what is each interior angle of a regular 17 gon? So now I'm asking for, like if we, this is a 17 gon, but if we went to a, I'll do my best here, regular pentagon. Now I'm asking for what is the measure of one angle? So how do we figure that out? Okay. If it's what? Okay. So I don't know if you heard Tim, but he said, first of all, tell me how many degrees are in a pentagon. Just grab your calculator and do that real fast if you can't do it in your head. This is a pentagon. Thank you, Julian. We're doing the pentagon just to warm up to this idea. So it's 540, right? 3 triangles. So 5 sides, 3 triangles, 3 times 180 is 540. Okay, so that's the total spread around 5 angles. So how do we figure out how much is in one? Just divided by 5, right? But what has to be true for us to be able to do that? Yeah, it has to be this word. That's why I stuck it on there. It has to be regular. Otherwise, if we have some wonky looking pentagon, right? Can we assume all the angles are the same? So that's convex. I keep drawing concave. Anyway, you get the idea. There's a pentagon of sorts. But the angles are definitely not all the same, right? That's the point. So it has to be regular, and then you just divide. But again, the thing that we can do is twist this around so that you solve for the number of sides. And I'll show you that in a second. But let's go write this next equation on here. Each interior equals 180 times n minus 2 over, what goes on the bottom? He said divide by what? The amount of angles, which is the same as the side. So what do we stick in the bottom? N. Okay. N is the number of sides again. But what do we have to add on here? Yeah, it has to be regular. You really can't overstate that. So make sure the problem says regular whatever gon.
If it doesn't say regular, what do we do?
You don't do the problem. Or you say, Mr. Atkinson, is it supposed to say regular? Like that. Yeah. No, not if it's just words. Yeah. So let's go do the example that we said. Okay, same process. I'm not going to write those steps again. So same steps as above. So we're going to write the formula. So this is each interior equals 180 times n minus 2 over n. This time we're filling out only the right side. So we have 17 and 17. And then just plug it in. So 180 times 15, what is that? Oh, it's 12 something. Okay, what was it? Sorry. What is the number? One what?
Oh, I didn't do that one.
Oh, you didn't?
Whole thing.
You're just doing that. 15 times 180.
Oh, 2007.
Yeah, 2,700 divided by 17.
Almost in the right thing.
Yeah, I thought so. Okay, so this time we have a fraction of an angle in each one. That's fine. No big deal. Now, what if I said each, just think about what you would do if I told you each interior angle is 158.8 degrees. How many sides is it? How do you solve for n then? I'm about to show you an example. So, there it is. By the way, there's a pentacontagon. That's a 50-sided polygon. What does it look like?
With dots.
So do you see why you would not go in there and draw triangles in that thing?
Yeah.
Okay.
We should. Just to see this.
It would be hard. I don't even think I could zoom far enough for that.
You know, there's like 3 minutes left of class. Might as well
Just try it.
That'd be
Oh, yeah.
cool.
There's not 3 minutes left.
Yeah, there's like a 10 minutes.
Yeah. All right. Go ahead and try this one, please. I'm going to pause there. Let's take 3 minutes to check.
Yes, we do.
3 minutes to check. Go. It's not freezing. Here's the algebra version of this, which I want you to be able to do. Where does the 172.8 go?
But we don't know this side. Oh, we're done.
How do we solve for n?
Insert the.
Algebraically, how do we do this?
We just solved it.
That way we don't have to guess and check. How do we solve for n? Okay. He's suggesting to multiply by n. You have to do it to both sides. Now what?
Do the 180 times the 180 times the
Yeah, you could divide by 180, that's true. Or you could distribute, either way.
We did the same. Is that for all equations?
Okay, how do we solve now?
Plus and 360.
Plus is not an operation. Minus 180. Okay. 7.2n. We're not dividing by 360. We're dividing by. Okay. Notice if you do it this way, you will be having negatives on both sides, and then you'll have to divide by a negative. But it should be positive, of course. So if you give me a negative answer, that doesn't make sense to have negative side lengths. So I'm not going to type in the negatives because they're both positive when we divide. Okay. So each of these, think how close that is to 180, to 180 degrees. That angle right there. It pretty close. Looks like a straight line, right? All right, let me show you what we're really gonna do in this class, which is this.
Yeah.
Oh, no.
It's not hard, it's just annoying.
Double it and give it to the next person.
Would you combine everything?
Double it and give it to the next? Crazy.
Okay. It says find the value of and the measure of each interior angle. What shape is this left one? It's a weird looking octagon. So how do we solve for x with this?
Figure out the size.
Probably figure out what X is.
What?
No,
Wouldn't it be 180 equals all those, but like together kind of?
So this has 180 degrees in it?
I'm just trying to throw out ideas here.
Good job.
Stupid idea.
Be nice, be nice. How many degrees does that thing have?
360.
More than one. Really? This
What? How'd you get 1080?
Like what you said.
She's right.
Am I?
Yeah,
Oh,
Wait,
well, you
what?
did 8 minus 2.
she's right. It's 1080.
Wow.
Said that.
Yeah, he said that.
Yeah, Micah said that a lot.
I was ignoring Micah. Actually, I didn't hear you, so good job. How did you get 1080?
He looked at me.
I have like
You what?
I have like a list of
Okay, well, tell us how you got the list. Like, what'd you do to get 1080?
well, since shape with 7 angles is 900, yeah, I need to do
Okay, so he's building off of a septagon. Guys, but we have the interior angles, right? 180 times n minus 2. But we have two sides of that thing. That's why I'm telling you to write both sides. We'll come back to this tomorrow. I feel like we're just